Hello everyone, in this video I'm going to be presenting my final term project for this course. Let me start my presentation by introducing about the content. My presentation contains 5 sections. In the first section, I will talk about the motivation for this project, and after that I will explain about the system description that I want to investigate. In the next section, I will present about the methodology that I used to achieve the task. The fourth session will be the simulation results, and the conclusion will be in the last part. So in the past decade, INS GNSS integrated system is one of the most widely used systems for localization and navigation. This system is popular because these two sensors have complementary characteristics. INS can provide fast measurement motion, while GNSS can provide high accurate low frequency measurement. However, GNSS is unreliable in some specific areas, such as indoor environment or areas surrounded by high buildings. In this case, the combined system could suffer position drift and give imprecise estimation results, as shown in Figure 1. One of the most famous alternative solutions for GNSS-denied environment and indoor applications is using camera, a lightweight and low-cost device that can provide rich content about the environment around the sensing platform. This video shows that we can get a lot of valuable information using a camera. From these points, we can either estimating the vehicle inertial motion, or we can even build a map around it. Despite this interest, cameras have a serious drawback, which is the scale ambiguity. Due to a lack of knowledge about the depth information as illustrated in the Figure 2. So in this case, we have to use another sensor which can help camera estimate or directly measure the depth. To solve this problem, we can use an INS that has an IMU which can measure 6 degrees of freedom, 3-dimensional position, and 3-dimensional orientation. For example, our laboratory uses IMU and camera to estimate the drone position in indoor environment. As you can see in this table, camera can measure position, velocity, and also the altitude of the platform with low frequency around 30 to 100 Hz, and IMU can give high frequency measurement. Therefore, these two also have a complementary characteristic and can be fused to obtain better estimation. In this project, we will investigate one of the state-of-the-art algorithm in the visual inertial navigation system field, which is multi-state constraint Kalman filter. This is an extended Kalman filter-based algorithm using tightly coupled structure that can compensate the biases of the IMU. Hence, the system can provide robust and accuracy estimation. The algorithm uses a bunch of camera windows to give a constraint of motion of the platform. And it has been proved that it has less computational complexity compared with SLAM techniques because we don't need to build the map. This method has been used in 2 virtual reality Google's project as well. So this is the structure of the algorithm. The image from camera will be processed to get the 2-dimensional position of the detected feature points and use it to update the estimation of the EKF. The EKF uses IMU model to predict the motion of the platform and also uses the estimate results to compensate the biases of the IMU. To impose the motion of the vehicle Every time a new image is recorded, the IMU poses will be used to calculate the camera poses. The KLT algorithm will be used to extract and track the feature point. When a feature goes out of the view, the tracked information will be used to update the ECAP estimation. The complete step is shown in the figure 5, and we can see that the complexity is only linear to the number of the features. To validate the performance of the algorithm, we generate a scenario that has a drone flies along a zigzag trajectory, observing static features using a downward-facing camera. The parameters that have been used to make the simulation are shown in this table. This is the altitude and position estimation of the MSCKF compared with the ground truth. We can see that the method can give accuracy estimation and also robustness because it can bound the error. This is the biases estimation of the accelerometers and gyroscope of the IMU. Overall, after 3 seconds, the biases are estimated correctly. Figure 9 shows the two-dimensional trajectory estimation, and we can see that the MSCKF outperforms the results of using only IMU. In this project, we investigate the possibility of using a camera and an IMU to estimate the three-dimensional motion of a drone in indoor environment. And we also apply and validate a famous technique using simulation. And we conclude that this system can be an effective alternative solution in GPS outage environment. So this is the end of the presentation. Thank you for listening. Goodbye.